Hi, everybody. Welcome back. This is uh, recording number 2. This will be on factor analysis. I'm going to try to keep the videos a little bit shorter than the first one. I think it makes it easier for processing and for doing things like closed captioning. So this one, I'll be around 15 minutes. Factor analysis. We're going to talk about some terms and definitions, and then we'll have subsequent videos. Probably going to end up being 3 or 4 on this topic to break it into smaller chunks. All right. So factor analysis. First question is why? Why are we doing this? The main idea behind factor analysis is what's generally called dimension reduction. One way you can think of dimension reduction is we're taking a lot of variables and we're boiling them down into 3 or 4 or 5 constructs that are represented by them. This is most common when we have things like scales. You might see a 40-item scale being boiled down to a set of 4 subscales, and that's generally the way we get those subscales rather is generally through processes of factor analysis. We'll have a lot of different definitions today. We'll talk about factors versus components, rotated and unrotated factor solutions, orthogonal and oblique rotations. We'll talk about some of the main statistics we'll deal with, which are factor loadings, communalities, and eigenvalues. And then we'll talk a little bit at the end about exploratory versus confirmatory factor analysis. So why do we engage in factor analysis? Again, the biggest reason is to take a large number of measures and make them into a more manageable set of constructs. For example, that 40-item scale that I mentioned, that might be boiled down into 4 different concepts that are represented by those items. Common thing that we're going to take a look at, we're going to take a bunch of measures of cognitive ability and problem solving, and we're going to turn them into 3 general components of intelligence. Factor analysis is very, very popular in terms of intelligence testing. Let me just bring up a web page. It's a web page here. And what we're going to do is take a look at a 50-item questionnaire. Give you an example here. This is a questionnaire. Some of you may have done something like this. It's got a variety of questions. I am the life of the party. I feel concern for others. I have a rich vocabulary. I'm interested in people. I am relaxed most of the time. I have difficulty understanding abstract ideas. You can see a whole bunch of questions here. I think there's 50 questions in all. These questions are individual items, and you'd never try to analyze all 50 of these individually. It would just be a really terrible way to analyze our data. What these items actually represent are 5 distinct concepts called the Big 5, or the Big 5 personality, and this is generally termed the Big 5 personality inventory. Those constructs that are represented are called extroversion, agreeableness, conscientiousness, emotional stability, and intellect or imagination. The way that we figured out what the constructs were that were represented in the scale was through using factor analysis, taking those 50 dimensions and in this case reducing them to just 5, what are called 5 factors. To go back to the PowerPoint. Oops. There we go. All right, so how does factor analysis work? Well, our goal in factor analysis is explaining variance, just like it was with regression analysis, except now we're not talking about explaining variance on a single dependent variable. We're talking about explaining the variance that is found on all of the individual scale items. We're going to create what are called factors to predict the scale items. Technically, that's what you would call a latent variable. We're basically making a variable that is trying to predict where people score on all of the different items. And what this allows us to do is to find clusters of items that tend to naturally go together, items that tend to be correlated with one another. Each factor is going to get a weight that's assigned to it, what's commonly called a factor loading, and that's the association between that variable and the factor. Large loadings mean that the variable is associated with the factor, that factor explains it very well. For example, some of the items on that scale that we just looked at, they're explained well by the extroversion factor, like I like to go out and talk to people. Those sorts of items are explained well by the extroversion factor, and they fall together with other items that are similar, like I love having conversations with new people. Items like that will tend to hold together. Ideally, what we'll see is a clear pattern where variables associate with only one of the total number of factors. That is, we're not going to see a situation where we've got ideally, we won't see a situation where we have variables that are highly related to multiple factors. All right, so some terminology here: factor versus component. There's two broad ways to reduce dimensions, and a whole variety of techniques, sub-techniques. But the biggest distinction here is factor versus component. We have two different approaches available to us. One is called factor analysis or common factor analysis. The other is called component analysis. Problematically, people often use the term factor analysis as a catch-all for both types of the procedures, but there are very clear differences between factors versus components. Although we'll see when we run these analyses, things don't look very different in terms of the statistics that we're interpreting, but there are some differences in terms of the results that we'll get. So the key differences here: factor analysis. With factor analysis, we do dimension reduction using only the variance that's shared between the variables. Component analysis uses all of the variance, regardless of whether it's shared or not. Another way to say that is that component analysis includes error variance that you wouldn't have included in the factor analysis. For this reason, components always explain more variance than factor analysis. The results from component analysis tend to look more impressive in terms of how much variability is being explained in the items. People have tended to use component analysis because of that. However, I would say that for almost any situation, the best practice would be to use a factor analysis approach rather than a component analysis approach. We'll talk more about the details there and the sort of differences that you'll find. But I think the main takeaway point here is that factor analysis is looking at what's shared between the variables, that should seem reasonable because we're trying to figure out what variables go together. Looking at the shared variance there, that's telling us, okay, this is the part of the variables that are correlated with each other. That's what we're looking at, rather than the stuff that can't be explained by the other variables. Component analysis looks at all of the variance, whether it's shared or not, and that gives you results that look statistically more impressive, but are probably far less stable because they're based on error variance as well. All right, factor rotation is another thing that we'll talk about. And again, with all of these pieces, we will go back and when we have some examples, we'll go and we'll talk about them in more detail and have examples to go with them. Factor rotation is a process that we use to increase the interpretability of our solutions, and the solution is just the results of our factor analysis, another way to say that. The goal of rotation is going to be to enhance variables association with a single factor while minimizing how strongly it associates with other factors. This makes it much easier to say, oh, okay, these items are agreeableness and these items are extroversion. It doesn't change the data in any way, it just changes the way that we look at it. Just as a quick example here, let's say we had a four item questionnaire. And we've got 4 different questions, and we're going to ask how many independent constructs are represented by them. And we can do this kind of graphically. One thing is, it could be that these 4 items are completely unrelated to each other. It could be that 2 of the items are related to each other, but not to the others, and the other 2 are related to each other, but not the others. So what we're interested in is how many independent constructs are represented. Sorry, so there we go. So you can think of each of these dots as or circles or ovals or whatever that shape is, as representing individual variables. Now, our goal with factor analysis is to explain scores on those variables. And you can see variable 1 and 2, variable 3 and 4. These, you can see very clearly that variable 1 and 2 are in the same space. By being in the same space, we can say that they're related to each other. They kind of cluster together. Whereas variable 3 and 4, they tend to cluster together. Whereas variable 1 and 2 don't seem to be very close to 3 and 4, meaning that there's some independence there. Now, factor analysis is generally represented graphically with lines that look like this. These are technically vectors. And what factor analysis is doing is it's trying to find the lines that capture the variability, capture where these variables are best. And you can see in this case, we have two factors, which I've labeled with those lines. You can think of these lines as trying to predict variable 1 and 2, trying to predict variable 3 and 4. And we can actually graph the explanation of variance on each of these in terms of the distance it is from that factor. We can see for this first variable where I've included this line. That's pretty close to the factor, so that would be an indication that it is correlated with that factor or strongly correlated. Whereas with the other factor, it's further away in terms of distance. Being further away is an indication that it's going to have a weaker correlation. It's going to be explained worse by that factor. We could do this graph for any of these items, but it's still the same concept. Now, ideally, what we're going to see is that variables are going to be very close to one factor and far from others. We can see with our second variable, the one that I didn't graph, the second one from the top, that one's about the same distance from both factor 1 and factor 2. So it's not an ideal situation. It's kind of the same distance from both the first and the second factor, which means that it's equally explained by those two, and we want it to be more explained by one. What we can do to get there is what's called factor rotation. Factor rotation helps us to interpret our factors a little bit more clearly. And what we end up doing is we end up simply moving the factor. You can see it's this, the dotted lines represent the rotation. All we've done is we've swung that on its axis like that. We've gone from it being an L shape to being on its side. We've swung that so that now we have the two variables on the top part of the screen very close to their factor, and the two variables on the bottom part of the screen very close to their factor. Rotation is a very commonly used approach that allows us to get a more interpretable factor solution, one that allows us to say the variable goes with factor 1, this variable goes with factor 2. So we'll talk about rotation, some of the techniques we use for rotation in more detail when we get to factor rotations. One thing about rotation is that it doesn't change anything about how much of the variable we're explaining, how much of the variance we're explaining. That all remains stable. It's just shifted in such a way that we have more attributed to as individual factor. And we can see here how we've maximized the distance between the variable and the factor that it doesn't go with, and minimized the distance between the variable and the factor it does go with. All right, types of rotation. There's two ways that we can rotate, or two general ways that we can rotate. The broad distinction here is between an orthogonal rotation. Orthogonal is a geometry term, meaning factors are at 90-degree angles from one another. Oblique is the other type of rotation. That's another geometry term, meaning that factors are not at 90-degree angles. I know everybody here loves geometry as much as I do, having taken it 2 or 3 times at least. So to put it in non-geometric terms, orthogonal means that the factors aren't correlated. We don't allow our factors to be correlated. Oblique, we do allow our factors to be correlated. Now, there's some tension here between what we expect in reality versus what is easier to interpret. Orthogonal solutions are generally easier to interpret. Oblique solutions can be messier. With oblique solutions, we tend to see variables associated with multiple factors. Orthogonal has been more common, and I think historically that was because they're a lot easier to compute. People used to have to do this stuff by hand, amazingly, back in the day. And then you would see a lot of, and then all of the published work that you see would use these orthogonal rotations, so it just kept reproducing itself. Oblique, however, is more realistic. If you think about the scale, subscale idea, you would be very unlikely to believe that a subscale was unrelated to, that subscales from the same overall scale were unrelated to each other at all, were completely uncorrelated. They're all measuring a general piece. For example, the Big Five personality inventory, you're measuring personality. Aspects of personality are going to be related to each other, maybe not particularly strongly, but it would be unreasonable to expect no relationship. Now, pretty much the thinking is that oblique solutions should be the default. They're more common, and we see packages like Psych and Lavon using oblique solutions as defaults. So it's probably a much more realistic way to think of it, even if you don't see this as much as you should. And just to show you graphically the difference between an orthogonal rotation and an oblique one, you can see here orthogonal, the factors are at 90-degree angles from each other. That technically makes them uncorrelated. Here with an oblique solution, the factors can be closer together. We get better explanation oftentimes that way, and this would represent some sort of correlation between our factors. So rather than forcing our factors to be correlated at 0, here the factors are allowed to correlate with each other. All right, a few statistical values that we'll encounter. First one is factor loading. Factor loading is basically a correlation between each of the variables. So if you've got a 40-item scale, it would be the correlation between each variable individually and a specific factor. So we're going to have one value for every variable on the factor. It's called a loading, and one way to interpret this is, bigger loadings mean something's more strongly associated with the factor, and ideally we'll see a cluster of items that all load heavily on one factor, have high scores, and they're correlations, so they'll be between -1 and +1, and have small associations with other factors. For example, if we have 40 variables and we reduce that to 4 factors, we would end up with 160 factor loadings. So a loading for every variable on each factor. The loadings are primarily used to interpret what goes with what variables are associated with what factors. So that's how we're going to use them interpretation-wise. Another statistical value we'll encounter is the communality. Communality refers to how well any individual variable is explained by all of the factors together. It's basically an R-square value from a you could think of this as an R-square value from a multiple regression, predicting each of the variables individually from each factor. So we'll get one value here for each of our variables, meaning that that 40-item scale we talked about would have 40 communalities, each indicating how well an item is explained. Low communalities mean that a variable is poorly explained. It doesn't fit with any of the factors, and this might be an indication that the variable's not really good fit for that scale. All right, eigenvalue is the third statistical value we'll talk about. This is an index instead of how well a variable is explained, but it's an index of how much variability a factor is explaining. And it's not on a specific 0 to 1 scale, but it can be converted to that for a proportion. The eigenvalue gets at how well that factor is explained, how well the factor explains all of the variables. For a scale with 40, with 40 items, the maximum eigenvalue would be 40, which would mean that a factor would be explaining all of the variables. So we can't really interpret eigenvalues outside of the context of how many items we have. However, we can take the eigenvalue and divide it by the number of variables we have, and that'll give us something akin to R-squared, the proportion of total variance explained by that factor. So if we have 4 factors, we're going to get 1 eigenvalue for each one. Much like with hierarchical multiple regression, factor order is going to affect the size of our eigenvalues. It's going to be bigger for the first, and subsequently it'll get smaller and smaller and smaller. Once we have a factor solution and we can rotate it, that'll even that out a little bit, but we'll still see that the first one is always going to be the biggest. Okay, just to swing back to factors versus components, the loadings, the communalities, the eigenvalues, they're all going to be larger when we're using components. That's because component analysis tries to explain 100% of the total variance. Factors always try to explain only variance that's shared by at least 2 variables. And that's going to end up being always less than 100% of the total. So we're going to have less variability available to us to explain when we use factor analysis instead of component analysis. But that's not a bad thing, because the stuff that we're not trying to explain was not shared. And we're talking about solutions that get at what variables go together. So the shared variance is probably the better thing to look at there. All right, one last piece of terminology: exploratory versus confirmatory factor analysis. Exploratory factor analysis is going to be an approach that focuses on how many factors are going to best explain our data. It extracts the structure of your, it creates a solution based entirely on the data. There's no theory or predictions guiding the process. We just ask questions like, okay, how many factors should I have? Okay, here's what they are. Doesn't necessarily have to make, the solutions don't necessarily have to make sense. They're not driven by theory. They're not driven by any predictions. Confirmatory factor analysis tests whether specific factor structure actually fits our data. That is, we have an idea of what goes with what, and we're testing to see if the data conform to that. This is a theory testing type approach, and you can think about this, if you developed a scale with 40 items, you might have some good idea about what you're trying to tap and the different constructs that you're trying to get at, and you would test that with confirmatory factor analysis. In terms of the handout, the biggest parts focus on exploratory factor analysis, and that's what we'll cover in the next however many videos, 2 or 3, but we'll also get into talking about confirmatory factor analysis. Ever since we moved to R, we've been able to do things like confirmatory factor analysis, which aren't available in programs like SPSS. You would have to have their commercially produced Amos program in order to do confirmatory factor analysis. And when we talk about confirmatory factor analysis, I'll also bring in a tiny little bit on structural equation modeling, which is just an extension of confirmatory factor analysis. So both confirmatory factor analysis, structural equation modeling, generally termed latent variable analyses. So we'll talk about those a little bit, just to show how we can jump from one piece to another. All right, that's about it for this video. In the next video, I'm going to focus on analyses and interpretations. I haven't written those files completely yet, so I'm not sure how much I'm going to have in each, but probably at least 2 or 3 short videos looking at exploratory factor analysis, and then a final one doing both confirmatory and structural equation modeling. And you can look for those hopefully in the next few days. All right, hope everybody's doing well. Hope everybody's washing their hands and socially distancing. Please be sure, if you have questions about homework, if you have questions about anything, definitely get in contact with me. For office hours, I'll probably be doing Zoom meetings of some sort. You don't need to be video conferencing there. You can, if you want, you can be on the phone. What's nice about Zoom is that if you had some, say, R code, you could share your screen with me, and we could discuss it. Anyway, all right, I'll talk at you soon.